the thing I need to say before we actually begin digging into this is I know many of you have met this topic already, okay? I just want you to forget everything you have ever heard about this. Just blank slate, okay? The biggest danger, especially with a class like this, is to approach this topic as just like a set of rules, basically. Set of rules, memorize the rules, learn how to apply them to, hundreds, thousands, maybe, situations, and then that's it, you know calculus. Nothing could be further from the truth, okay? The design and the use of calculus is such a creative process that to just reduce it down to, okay, like you will learn rules, but if learning rules is what calculus is to you, then you don't know what calculus is, okay? So now, pick up your pen, and let's think about what this is. Calculus is actually an abbreviation. The full name of calculus is infinitesimal calculus. Now, the reason why, this is what we're actually going to be doing, infinitesimal calculus, but as you can see, it doesn't exactly roll off the tongue, okay? Because it was such a long, awkward phrase, calculus is just what it came to be known. But that's a bit weird. Calculus is a very general word. It's the same word where we get the word calculator from, and calculate. In fact, before the 1600s, calculus, if you said calculus, that would basically mean the same as maths. It's calculating stuff, right? The reason why calculus means maths is because calculus, it's actually a Latin word. It means, it's Latin for small pebble. And you're like, what does that have to do with anything? And there goes my small pebble. Small pebbles are what were used to calculate with in the early days in ancient Rome, right? They get a whole bunch of small pebbles, right? And some smart guy in some country, I don't know its name, put all these pebbles on like rows and move them around and call them an abacus. Okay, small pebbles are what are used for counting and for calculations, right? By the way, it's also where we get the same word chalk, calc. You get it? And in fact, if any of you ever become calcium, that's exactly right. If any of you become dentists. Or go to the dentist, they might say, oh, you have calculus on your teeth, which by the way, not a good thing, because you're not meant to have small pebbles on your teeth. Like it's all of the gross stuff which is not meant to be there, and it's damaging your teeth, okay? So calculus, right? It's really this word for calculation, and the fact that it took over, like what we're about to do, this little subtopic, it took over from, like, can you imagine, like, okay, mathematics is a really, really big word, right? And if just one little topic in mathematics became called mathematics, right? What does that say about all of the other things, right? It says like, this is really, really important. We have many branches of mathematics, right? Calculus is just one of them. Each of them is sort of keyed into one single big idea, okay? You think about this with me. Geometry, for instance, we're familiar with geometry. When you think geometry, you think shapes, right? You think shapes, things that take up space, right? Shapes, plane, and space, right? That's what geometry is about, like dimensions and all that kind of thing. Algebra, this is a bit trickier, right? But all those x's and y's and pronumerals and unknowns, what they're really about is quantities that are related to each other. Things that change together in proportion to each other, in inverse proportion to each other, all those kinds of things. If they're related, then algebra will help you understand it. Probability, that's a bit of an easier one. It's the mathematics of what? Chance, uncertainty, right? When you're like, I'm not sure if something is going to happen, but I can know like the basics of like, this is more likely to happen, less likely to happen, am I going to win the lottery or not, am I going to get an ATAR of 99.95, etc. Okay? Each branch of mathematics has its key idea. Calculus is the mathematics of all things that change. All things that change. And you know what? There's lots of things in the world and in the universe that change. So you can kind of imagine why calculus kind of took over. In fact, number one, the preliminary and HSC courses that you're doing, Mathematics and Mathematics Extension 1, are called the calculus courses. They're a good 70-80% plus calculus, and it's like subtopics. Okay. In fact, the equivalent of what you guys are learning in America is called AP Calculus. The AP stands for Advanced Placement, right? It means where you guys, we don't mess with you guys. You guys are serious about your maths. Okay. The course is called Calculus, and in some ways, like, so is ours. It's just not given. It's yeah, that's right. There's pre-calculus and then there's calculus, right? It's like this is the things preparing you for this. Okay. Now, calculus, you need to know. It was developed not jointly but independently by two guys in two countries at exactly the same time, and there was a huge argument between these two as to who invented it. By the way, before it was called calculus, it was called the calculus. The B is like a capital C calculus. The two guys are one who you might have heard of, a guy named Isaac Newton. Guy in England, right? You might have heard of him. The other guy you will probably not have heard of, Gottfried Leibniz. Okay. German guy, Newton in England, Leibniz in Germany, and both of them simultaneously developed this big idea. Okay, and I'll tell you later on when we get to it. You can remind me why it's unusual that no one's heard of Leibniz and everyone's heard of Newton. Okay, so here was the problem, and this is the famous part that they were each trying to work out. Okay, so Newton was sitting under a tree, right? Or so the story goes, right? And he saw the apple fall from the apple tree. It fell to the ground. Right?
Is that why you actually work in his papers?
No, that's not what happened.
It's a story. The apple fell to the ground. Where it actually hit is up to debate, or whether it was an actual apple or not is up to debate. But the point was that he watched the apple fall, and he watched it fall to the ground. He's like, oh, okay, gravity. Gravity's a thing. It makes the apple fall. But then as he watched the apple fall, he thought, the moon is way up there, right? And it's also being held in place by the same thing that makes the apple fall, right? Gravity. But it doesn't hit the earth. Why does it not do that? Why does gravity do this to this object, but that object just stays way up there? And he's like, how do I work this out? Right? So what he did was try, as we've been doing, to take a problem which you don't know how to phrase and turn it into a problem which you can phrase, because then you can solve it. He ran into a problem. Gravity does something unusual. It does something like this. Gravity, like most forces in the universe, is inversely proportional. The force that it exerts on something is inversely proportional based on the, I was going to say the distance, but it's really the square of the distance that you are away from something. Okay, so the further away you get from something, so if I have over here distance, right? As your distance increases, the force of gravity, and well, actually everything really, if you think of the electrostatic force, it's Coulomb's law, I think. It gets smaller and smaller and smaller, and it drops off like this. Okay, it drops off quite fast. Okay. Now here was his problem, right? He was trying to work out, okay, how do these things relate to each other, right? How does gravity change over distance, right? This is the problem he was trying to solve. And this is tricky because this thing is changing at different rates everywhere that you look, right? For example, if you just compare it with a straight line, you can draw one of these for me, okay? For a straight line, if you want to know how this straight line is changing, okay, that's not hard to work out. You just think, for example, at a particular point in distance or time or whatever value, you compare it to another point. Okay? And if you've got 2 points on there, you can just say, look, I'll just compare how much it changes in one quantity versus how much it changes in the other. And you just get them as a ratio, right? We know that ratio by the name, starts with a G. Gradient, right? On a Cartesian plane, you'd say, look, this is vertical, so you call that rise. And this is horizontal, we call that run. Okay? And the gradient, which it's m, still who knows why, okay? The gradient is just the ratio between those two things, okay? But there's a problem here, No matter which 2 points you pick, you're always going to get a different value. See, the thing about this, the reason why this works, is because I can calculate that, or I can calculate between these 2 points, or I can calculate between these 2 points, and you're always going to get the same value. Right? You always get the same gradient. It's going to be this constant, right? We know how to read that off. But here, we have some trouble. Here we have some trouble. So here is what Newton did, and it's ingenious. Okay? Think about a circle. Okay? Yeah, I've done better. All right. Now, what he really wanted was how much am I changing at any given point, right? Now, by gradient, you guys already know in terms of like geometry, like what does that look like? It's the steepness of the graph, right? If you can know how steep something is at a given point, that's its gradient. Okay? So he wanted to know, like, I know obviously it's steep over here and it's not so steep over here, but how much? Okay? So what he was really after, the quantity he was after, was the gradient of the tangent. Okay? This is a really critical idea, right? The gradient of a tangent. The problem with working out the gradient of a tangent is that gradient is rise over run. You have to have some run. You have to have 2 points, right, to compare between. y2 minus y1 over x2 minus x1. You need a y2 and an x2. But a tangent, by definition, doesn't have 2 points. It's just got 1, right? In fact, that's why it's the word tangent. Does anyone know, just like all of this, right? We have another word in our English language which comes from the same root as tangent. Does anyone know what it is? We don't use it very often, admittedly. Tangerine. Tangible. What does tangible mean? It means you can touch it. You can touch it, right? So a tangent is something which just touches 1 point. Okay. So this presents problems for us and Newton and Leibniz trying to work out what's the gradient at that point, because there are no 2 points to compare by definition. So here's what they both did.